get to it. All right, the recording is on. All right, before we get started with the intro today, we have our starting soon / elevator music mode Mike Driscoll Python pop quiz. Mike Driscoll is a former guest speaker of CalPy, once SacPy. I believe it was SacPy back then. Hopefully we can get him back. He did some pretty cool stuff. He's an author many times over. So we've got number 73 of the Mike Driscoll Python pop quiz, indexing indignation. Okay. So let's see. Do we have any guesses in the chat for what this output is going to be for this odd code? Let's see. Oh, all right. Divium's back. Oh, no, he was here for a moment. Any guesses? Aaron says C, the list from 0 to 9. Okay. Erwin concurs. All right, so let's see. We're defining a class, and we have a class variable integer. I'm setting it to 0. And then we define a gender method using self. And internal int is established as the class's integer value, which we know to be 0. And then we're incrementing the integer to 10. And then we return that integer. So we've got 0 now at 10, and we're returning that. So then we go and we do one of these list comprehensions. X for X in range number to number. Okay, so number to number.
You're covering the key part of the question.
Right? Man. Yeah, I guess I could turn off my video. That maybe would make it easier. There we go. Oh, much better. Okay, so from number to number. So we're saying we're hearing 0 through 9. It seems like maybe an interesting option because I'm giving it a range. Now referencing that class variable by just calling number. Well, I don't know. Anyway, let's look at it. Do we have any more guesses before we open up the terminal? Oh, increase the font size. We don't like tiny font. All right, Aaron and Erwin, see how it goes. Okay, so
I think it's an empty set.
It could be because range potentially from 0 to 0. Well, I guess we're about to see. Let's make sure we don't have any typos here. Integer looks good. Index gender, pretty good. Internal int. All right. Any last guesses before we go? Andrew says empty list. Ross says empty list. Oh, C was correct. Awesome. All right. We got a winner here. Okay, Robert has some commentary here. Robert, you want to walk us through what you got there?
Yeah. So the trick is that the range what calls number, right? And whenever a function or a class needs to return numerical value, it calls dunder index, right? So so it's calling number twice, and the first time it calls the dunder index function, the value returned is going to be 0, right? Because internal int wasn't incremented. It was number.energy that was incremented. So first time, second time it's going to return, right?
What was that? Sorry.
What?
Sorry, my friend's in the background watching the football game. He's a big fan of the Broncos. Go on.
Yes. So one key is that earned by the dunder index, and that doesn't get implemented during that function, right? But it will be incremented the next time.
Aaron's got some commentary too. The following would have the same result and number print x and range of an n. Aaron, do you want to comment on that? All right. Well, yeah, a bit of a red herring. I agree. Robert says he did cheat a bit. Okay, he's got a grok link for us. See what grok says about it. Aaron, no, we can't hear you. Maybe your mic is a little funky or something. Your hair
better?
looks luscious though. There you go. Yeah, got you now. You're coming through.
You can hear me now.
Yep.
Yeah, I was saying nothing happens at class initialization. All the action is on this class variable. So all that matters is the number of times globally any instance of number has been interrogated for its index.
Okay, so by referencing it a second time, we're now calling that under.
Yeah, and it doesn't matter which number instance you're referencing, because the only thing the index method does is retrieve and modify this global class variable.
Well, as we know from Mike Driscoll pop quizzes, if you did this in your code, it would basically be a war crime, as Johnny likes to put it. But he always has a clever way of demonstrating some funny ways that things get interpreted.
If we were to copy Aaron's code,
What was that?
if you wanted to copy Aaron's code, n equals number, and then
Oh yeah.
Yeah,
Sure.
but you have to redefine the class, or you'll get a different answer.
Oh, I see.
Because the class now has whatever it is, 20 as its internal value. But if you redefine the class, then it'll reset everything.
Okay, and so then you're saying for the print, now we go n equals number, and then print x for x in range n.
Yeah, I believe you'll get the same result.
Yep. Right, good call. I guess that makes sense because we're just sort of referencing the class there, the instance.
Yep.
Nice. Well, Mike is right. I'm indignant. Horrible. But I think we got to the bottom of that one. Ian sometimes is with us. I think he's contending with some connection issues presently. So, might as well continue on with the intro.
Actually, Aaron's code is even less intuitive because you think that because it's a variable, and you're not explicitly reassigning it, it's not going to change. but really it's a point. It's going to be a pointer to.
Yeah, I mean it's badly written code because the index retrieval method has side effects, and that will surprise anybody who uses this class.
Oh, Robert, I was trying to pull up the Grok thing, but I think maybe I don't have the right account level to look at it.
Okay.
That's it.
It's kind of hard for me to paste all that right into the chat.
Yeah, no problem.
It did a really good analysis of it. I just copied the screenshot. I said, explain this.
All right. Well, we're already 10 minutes into this, so I don't want to eat up too much more of Marcel's time. So we'll get on with the intro, and then let the man do his thing. All right, little humor before we kick it off. We finally made it. The most Python 3.14. I guess 3.14.1 might be a little bit more Py-ic, if not Pythonic. Yeah, right. Aaron, 3.1415. Yeah, maybe they should just never go past 3.14 and just keep adding integers to the end of pi.
It's like Tech, the typesetting software by Don Knuth. So it's at like version 3.1514159 or something like that, and he releases versions so slowly now that every new version he just adds a digit of pi to the end. And he said when he dies, then the version of Tech will become pi and be permanently fixed to pi. So,
committed to infinite iteration. Good man. All right, welcome everyone. This is the November edition of the California Python User Group Meetup. We've been online since 2020 when Robert and I took things over. And we found our opportunities to meet in person back in the founding place in Sacramento, but most of these days we just do it with the organization that is sort of the parent group, SacTech. If you're in Sacramento, towards the end of the month, they do an in-person at, I think it's called Hop Yard. It's pretty cool. So a whole bunch of different groups show up. But CalPy has been sort of a branding pivot for various reasons. One, to establish a little bit more control over the branding, and two, to integrate a whole bunch of other Python user groups in state. And so myself and a handful of others show up to various other groups, especially San Diego Python on the weekends on Saturday. It's a study group, pretty fun. They meet over Discord. And usually read the code of conduct if the previous meeting was a little spicy, but thankfully it's been pretty chill. But generally be cool. I'm not exactly power hungry, but I'm not here to allow people to mess with other people's time. And we adhere to the PSF code of conduct as well. Still working to steer ourselves under the PSF umbrella on the Meetup Pro network. Apparently they have some issue with the fact that I had to start a new pro network, but we'll work through that. Hopefully that'll happen sooner rather than later. But yeah, the community is pretty straightforward. You know, we're here to be open, focus on what's best for the community, acknowledge time and effort, be respectful of differing viewpoints and experiences, show empathy towards other community members, be considerate, respectful, gracefully accept constructive criticism, and use welcoming and inclusive language. And I think by and large, the group has done a pretty good job of that. So thanks everyone, keep it up. We are on a handful of different social media or communication platforms. SacTech runs a Slack. You can find them https://sactech.com. They have a little bit of a terms of service to log in, but we update things there. If you're interested in other tech than Python, which I'd recommend, Python's a glue language. And so if you want to know something about JavaScript or AWS, SacTech's got a whole bunch of them under their umbrella. And this also has a Discord channel, and my company, Brazen Studios Discord server You can get an invite there by going to http://calpy.org. Hope to see you in there. If you join tonight, I'll add the the CalPy handle to you, or you get updates as it goes along. We're also on X. We've got the dunder for CalPy on there, and post updates there, and we've been finding a good amount of speakers through there. It's been pretty fun. We're also on Reddit. It was StackPy. I think it's CalPy. I have to say, Reddit kind of freaks me out. Every time I post any of the events there, we get people Zoom bombing, and the subsequent meeting, we got to read the code of conduct. LinkedIn, it's a good place to get those. Take a screenshot and get the QR codes. We've got a group where we post events as well. We cross-post everywhere, Facebook as well. And once we're done with this will be published to the Brazen Studios California Python user group playlist. Check it out sometime. Well, like and subscribe, and check some of them out. We've had some pretty neat ones. Everything from literally people doing an active tutoring session where we walk them through things like learning dictionaries, all the way up to core contributors like James Powell and some familiar names like Travis Oliphant of SciPy, NumPy, and Alex Martelli of Python in a Nutshell, in the O'Reilly books. Meeting format's pretty straightforward. Please don't hold your questions till the end. We like the inline conversation. If you're not feeling confident about speaking up inline, you can raise your hand and I'll do my best to call on you. And also you can make a comment in the chat and we'll do our best to make certain that is addressed as it comes up. So, if you're going to unmute, please make sure it's not too noisy in the background. If it's noisy, please mute back up. Some people will sound bomb with true intent, and Marcel, I promise to moderate efficiently. So we do a quick screenshot. So I'm going to drop the share here and put it in gallery mode. How do I drop the share? Oh, I see. Drop that. Gallery mode. Anyone who's willing to jump on? All right, we got our mascot there. Twinkles, the green cheek conure. All right, Ferdy's on. Awesome. Oh, we got Carter too. All right. As my father used to like to say, look intelligent. And then some photographer told me if you want to get a good angle, point your chin at the camera. Awesome. Okay. So we get to the rest of the show. We'll do a bit of an intro and then let Marcel take it away. And we'll drop the elevator music. Don't worry, Marcel. All right, so we have the pleasure of hosting Marcel Kornacker of Pixeltable tonight. He's got a number of pretty epic accolades. He's one of the inventors of the Apache Parquet format.
Oh, wow.
A former Googler like myself. And he put together a really neat open source project called Pixeltable that takes care of the plumbing for AI projects. And that is what his presentation is going to be tonight. Thanks again for setting this up, Rob, aka Lux. And Marcel, it is your time to take it away, sir. I'm going to drop the share so you can take it over. Oh, apparently something good happened in the football game.
Block punt.
A block punt, I guess. All right, Marcel, you should be able to share. The floor is yours, sir.
Okay, thank you. Let's see. That is interesting. All right, let me try this again. Second. Okay.
And we'll edit out any noise and awkward pauses. So take your time. It'll look
Good.
nice and snappy in the end.
I am, all right. Somehow, maybe Google Slides full screen mode doesn't quite work. Let me try this
It would
differently.
not be a proper demo without some glitches.
Yeah, yeah. All right, once more. Okay, here we go. All right. Well, now we have more borders. Yeah, thank you for, attending a talk about Pixeltable. I will quick intro about me, co-founder and CTO. The other technical co-founder, Aaron, is also on this call, and then our CEO, Pierre, is in Seattle. I, just like Aaron, have a PhD from Berkeley, myself in databases/computer science. I was at Google from '03 to 10, was the tech lead for the query engine side of the F1 database. And when I left Google and joined Cloudera, I was created the Apache Impala project and was also the co-creator of Parquet. So, and then got interested in, I want to say, AI, ML, a few years back in the context of computer vision, and that was sort of the motivating, I want to say, event for then starting Pixeltable about 3 years ago. So that's the genesis of that project. And what are we trying to do? We're with Pixeltable, we're trying to address the problems with AI development today. And by AI development, we mean creating products utilizing AI models, in particular for multimodal data. And here's an example. If you want to make your collection of videos searchable, what do? There is typically a lot of this is done in the Python ecosystem. There is every inference service has a Python SDK. A lot of this is done in Python and started in Python. And so there's a lot of open source packages out there to help you with working with videos and making them searchable. So FFmpeg is, obviously a standard. Like I said, you have endpoints such as OpenAI. You have open source indexing, embedding index formats such as LanceDB as an example. And you can also talk to Postgres and put your structured data into Postgres utilizing things like SQL Alchemy. But the problem is that if you try to wire all of that together, you have to write a ton of custom code to take data out of one place and shove it in the next. So, FFmpeg will create, video files for you. You have to drive the OpenAI Vision API yourself, and so forth, right? So there's a lot of code to be written to put something fairly simple together and make that workable. So typically you write, lots of glue code, and even after you do that, there's still, if you're now trying to turn it into a product, there's even more work, right? Reproducibility, performance, and so forth, failures, retry, etc. So this is a made-up statistic, but based on personal conversations, I would say it sounds about right. So when you're trying to develop products utilizing AI technology today, a lot of the development is going to end up with you writing the glue code that moves data around. So, and, pipelines and so forth. And so what is the problem here? When you look at multimodal data, you are typically dealing with data that is, you have objects such as videos, documents, images, etc., that live in object stores. You might want to use embeddings for similarity search that live in a vector index such as Pinecone. You probably have metadata and other structured data that sits in Postgres. So you have a lot of different kinds of data and different storage systems for that data. For a lot of things, such as if you want to do anything with images, you have to load them into memory and then maybe use PIL to manipulate the images. you have to track manually where the data goes, right? All the data that your application deals with lives in various places, and you need to write more code to tie it together. And after you've done that, you're still missing a lot of things you need when you write applications, right? So you would like to have transactions so that when you're doing a sequence of transformations or model invocations, you have data that stays consistent. You don't have partial results. You often want multiple users to interact with your system, especially if it produces data. You want the transformations to be persistent. You don't want to have it do it in memory and then it goes away at the end of the session. And you typically also want to do things if you write applications at a granularity that is not done in batches, right? So you want to do it one row at a time, oftentimes. So this is what you're usually dealing with on the storage side when you're creating AI applications. And there's also the orchestration piece. Now you need to actually run transformations and do model inference and so forth. And so you now need to write the custom code to wire these things together. Let's say FFmpeg output, and you take that and try to shove it into an OpenAI Vision API endpoint. You want to run things maybe in cron jobs because you need to have stuff done every once in a while. You are calling external endpoints and have to deal with rate limits, and you get failures. You might need to do retries and so forth. There's a lot of complexity in dealing with all of these things and creating something that can actually run a sequence of requests, and then you end up with the correct output that you want. And once you do all of that and you're done with it, then typically your product requirements change. Every time you develop products, things tend to change after a while, and then you start over, right? So here, when you're doing this manual orchestration via scripts, um, what you don't have is that you're able to track what depends on what and maybe see intermediate outputs. If you want minimum latency and maximum throughput, you have to put a lot of effort into parallelizing calls, in particular to external endpoints and so forth. You need to do failure handling and maybe store the error conditions you got so you can retry it later. And you also have potential problems with operational integrity, such as if you use inconsistent models for indexing and querying, right? You creating embeddings, you put the embeddings into a vector index, and if you accidentally mix up models, you end up with a contaminated index. Or if you accidentally use a different model for the query, you will get incorrect results. So there's a bunch of pitfalls here that all require a lot of effort in creating a system that runs dependably and in production. And I've been talking for a while, so I'll stop here and see if there are any questions.
So the one thing that stood out for me was PIL. Now, we had Jeff Clark on previously, the pillow guy, which is a fork. Is
Yep.
that, are you working on the default PIL, or is that pillow?
Yeah, it's using the regular pillow, the whatever
The latest one.
most common. Yeah, exactly. And so we do support pill operations on image data, which we might demonstrate later. I'm not totally sure, but if not, we'll squeeze it in somehow. Um, so looking back, what is actually the problem with this approach, right? You have storage, you have data you need to store, and you have orchestration you need to write. And how is that really a problem? And here's a little cartoon that illustrates it. And I think it's very telling and also very true that by and large, if you do this by hand, you end up with something that tends to be very brittle and tip over if as soon as requirements change or the environment changes in some form, right? So it's basically a bad way to string together this kind of functionality. And so the real problem as we see it is that you're dealing with data and the orchestration piece as two separate systems, right? Typically, you often have things, orchestration frameworks like LangGraph that allows you to string together a bunch of operations and then dump the data out into some other places. And then you have data storage systems such as a vector database that takes the output of that and then is able to do retrieval on it, right? But the problem is really that the two sides need to be wired up by hand. And so having to do that is painful and error prone and also not really necessary from our perspective. So Pixeltable is in essence a database system that knows how to create data or an orchestration system that knows where to store the data. So it includes both storage and orchestration and retrieval. And that means that all the data that is stored in Pixeltable is also usable as inputs for your orchestration steps. And all the output of orchestration steps are, again, stored in the database system. So it's basically a table structure that is able to capture both the computation as well as the inputs and outputs of the computation. And here is an illustration what that looks like. We're going to do a demo at the end, so we'll make that more concrete. But just for illustration purposes, right, you have here a Pixeltable at its heart is a database system that exposes data through a table API, both data and the orchestration piece. And so here you have a table that contains a video column and contains columns with video clips. So Pixeltable supports data types such as document and video and audio. And you have computed columns such as this one that extracted the audio. And now you have a column that contains the audio for a particular video. And you can now also add more computation, such as transcription of the audio into text using a particular model, such as Whisper. And now you have a bunch of text, and you might want to summarize the text with another model. And so here you have a computed column as a summary and so forth. And then obviously you can take the summary and then also run it through another model that outputs embeddings and so forth. So basically, you have data here organized into a table, and there is a whole bunch of computations and transformations happening on that data, and it is all expressible in this table API. And we're going to look at a concrete example now of what we alluded to earlier, which is to index the contents of videos. And so what we want to do here is starting with a video, we would like to get the audio out of it and index the audio, maybe even using embedding models that are audio specific. We want to take the audio and transcribe it and also index the transcript with appropriate embedding models. And then we also want to take the frames out of a video and index that as well with also embedding models such as clip that allow you to map images and text into the same vector space. So at the end of that, we should have basically a system that, given a video, is able to break it up into audio chunks, these guys here, and take the audio chunks and transcribe them, and then let's say summarize them or embed them, and also take the video and extract the frames, and then also get embeddings on that. So basically stringing together this somewhat complex pipeline so that at the end of it, you have a bunch of vector indices that you can then use for similarity search.
And for people following along, I'm placing links in the chat that pertain to the tech that Marcel's referring to.
Okay, so how do you do it in Pixeltable? You start out with a table that contains your videos. As I said, you have column types that include video. We will then extract the audio from the video and also get a transcript of the audio. And we will do that as computed columns. So you have one table here that contains both a full audio extraction as well as a full transcript. We will then add a view on top of that table. And so a view basically, if you're familiar with relational databases, they're all exposed views. A view is a derived table. And so now we are deriving a table that contains chunks of the audio of each of these rows. And so in Pixeltable, there is also a concept of iterators, and in particular, user-defined iterators. So the idea that you might want to break up something larger into smaller pieces, such as taking an audio file and breaking it up into fixed size chunks. That's one iterator. We also have iterators for iterating over the frames of a video, or we can iterate over chunks of a document, which is not something we're going to illustrate. But typically, if you work with documents, you will often want to break them up into pieces as well to do some processing, such as embedding or indexing the pieces. So here we're looking at views. The first one creates chunks out of the full audio that was extracted from the video. The second one then transcribes the chunks and and then adds an index on the transcript. And the third view gets the frames out of the video and then also puts an index on the frames. So this is kind of a high level overview of how you would solve that pipeline problem in Pixeltable.
So Stephen had an interesting question about how reliable Whisper is on the transcripts, and then specifically, how does it handle onomatopoeia? Like if there's a bang in the background, does it do that, or is it purely?
I'm not completely sure, honestly. You're not tied to Whisper here. You can use any transcription model you want. So again, Pixeltable is not really trying to get you to use one particular model or another. So if something better comes along, you're free to use that as well. But I don't have a particularly lot of experience with running Whisper, actually.
Right. Yeah, this is more about the way it orchestrates, and this is just a concrete example.
Yeah, exactly. Yes. So so what happens now is if you define this table structure, when you now add a new row here with a video, it'll automatically run through this whole view setup that you define. So the views are in essence virtual tables that are defined logically, so to speak. And the Pixeltable stores all of the metadata and understands how one view depends on the base table and is now able to then propagate an insertion of a single row throughout all of the views that are defined on it. So it will basically compute all of the computed columns and then also fill all of the views that are defined on the base table and even transitively, right? So you can stack the views, and in this case, it will take the audio and chunk it, and it will then take the audio chunks and turn that into a transcript and then split that up as well. And we'll see a concrete example of that in a little bit when we're going to do a demo with the actual notebook. And so here, a little more about Pixeltable in detail. So first of all, really, what is it, or who's it trying to address? Who's it trying to speak to? What is it trying to address? Users are typically ML engineers or AI engineers nowadays, data scientists, basically engineers who are building AI-based data products. And the goal here is that Pixeltable will do all of the data handling and orchestration for what you're trying to accomplish. And so that you, as an engineer, you do not have to spend time on engineering the data plumbing pieces of what you want to do, right? And so typically that tends to be the least rewarding aspect of creating AI-based data products. And it's also very complex and time consuming. So the design is basically centered around a table abstraction. So all data and transformation logic is expressed as tables and table structures. That means that the data interactions are declarative. You can simply refer to columns and other things in the row when you want to define a new computed column. And we'll see, like I said, concrete examples in a little bit. But it doesn't limit what algorithms what algorithms or models you can run. So again, if there's a better transcription model than Whisper, then by all means do that. If you want to do evals and there's one eval practice A and eventually there's a newer eval practice, you can easily implement that in Pixeltable as well. Um, Typically when you do evals, you will need to basically store multiple versions of something and then do a comparison between the versions, right? So something that a table structure is very suited for. And what is Pixeltable today? Pixeltable is available as open source, an open source Python library with a friendly Apache license, and will soon be complemented by a cloud service. So we will be launching our data sharing service soon, and we'll again show examples of what that will look like later. But you can kind of think of that as GitHub for data tables, for multimodal data tables. I'll take a quick break again to see if there are questions. Okay. And so this is what you get when you install Pixeltable and then run it. Pixeltable is like I said, at its core, it's an OLTP database system. It utilizes Postgres under the covers for structured data, but it gives you basically transactional semantics for data that includes multimodal data, such as videos and audio, etc. Basically things that live in files. So the Pixeltable runtime system consists of a catalog component which records your metadata, so it understands what your tables look like, and in particular, how computed columns are computed. And the runtime system itself consists of a planning piece that is able to take a query or an insert statement, and we'll see what they look like in a little bit, and then turn it around into a sequence of operations that do retrieval from Postgres and augment that with execution logic in Python directly. So it's able to look at all of the computed columns in your table and determine the order in which expressions need to be evaluated and so forth. So, and there's also an async execution piece in there that is able to parallelize your calls to endpoints such as Anthropic or OpenAI and so forth. Pixeltable allows you to refer to data that's sitting in object stores. And so there is a cache component in there as well that will transparently download media data from object stores and now also actually upload it. So you can have computed columns that produce media data such as videos, and then have Pixeltable also take care of the upload into your object store bucket if you choose to do that. Again, if there are any questions, feel free to interrupt. I am now going to go through specific Pixeltable syntax to illustrate the various aspects of the API. So the first thing is, like I said, Pixeltable is at its core a database system that stores multimodal data. And so that means that all data sits in tables, and the tables are persistent and transactional. So it's not like a data frame abstraction like pandas or polars, where you need to figure out where to put the data afterwards or to load the data into the abstraction. In Pixeltable, all tables are persistent and transactional. Also, the tables do not need to fit in memory. So this will scale to data sets that exceed what you can fit in memory, right? So, and this is particularly important with things like video, which can quickly get to very large sizes of whatever it is, frames, etc. Because you want to deal with multimodal data, Pixeltable has an expanded set of data types compared to a relational database system. So you also have media data such as documents, videos, images. There's also audio, and there is also array and JSON. So basically NumPy arrays and JSON structures can all fit into a Pixeltable table. And so here you see some syntax on the right-hand side. It's all available through a Python SDK, and Python is basically used as a domain-specific language. So here we're creating a table that contains a single column called video with data type video. And then we're inserting a row into the table that is a local MP4. So, and we'll again see an example of that later, where we're inserting actually HTTP hyperlinks. If you want to store data, you also want to retrieve the data. And so again, Pixeltable gives you a comprehensive query language. So you have standard relational operators such as select, where, and join. Aggregation is possible as well. And you have meaningful extensions that utilize the augmented data types, such as for JSON, you have path expressions, and transformations on JSON. And the idea being that if you want to interact with the data, there is no need to dump out the data and then write a script that iterates over it. You should be able to express all of your data interactions in Pixeltable directly. And the way this is executed is Pixeltable looks at the query. In this case, on the right-hand side, it's a very simple selection of a few columns of the video table with a selection predicate. And so what it'll do is it comes up with an execution plan that tries to do as much as it can in SQL. So it will translate this selection predicate, which we'll look at in more detail later. It'll translate that into SQL and run that directly and get the underlying structured data. And then it'll augment that with whatever is needed for making that available in Python. So that in particular means that if you have image data and you query it in that way, you get it back as a pill image, an in-memory pill image. So in this case, we are running a query and we are seeing here the audio chunk, a sentence, which is a string column, and the video itself. And so you see this here. And again, we'll see it later in the demo that you getting a playable video output. Orchestration. We talked about the storage and the database side of Pixeltable. There's also the orchestration piece. And the way it works is that all execution logic is expressed as computed columns. So you basically add computed columns to the table and they encapsulate whatever logic you want to run. So here on the right-hand side, we have a table with videos, and we are adding a or in this case, it actually contains audio chunks. So V1 here has a column called audio chunk of type audio, and we now want to get a transcript, and we can do that by adding a computed column that invokes the OpenAI transcription UDF. So Pixeltable comes with a host of user-defined functions, in particular for all of the popular inference service providers. We have pre-built UDFs, but you can just roll your own. They are, for the most part, relatively simple. And what this will do is define a computed column that will then, every time you add a new row to this view, it will populate the transcript column by invoking the transcription endpoint. You can now also, what this returns is a column of type JSON, because you don't get just a transcription text back, you also get some other stuff back. And here we added another computed column that is a JSON path expression that simply gets the text field out of the transcript result and casts it to a string. So here we have a string column with just the transcription text. And so when you look at the bottom here, when you look at the schema for that view, you see, whoops, it's got cut off, and we we actually don't see the transcript and transcript text column, but we will see that later in the demo. So little glitch here, but that's okay. Another aspect of orchestration is often that you want conditional data flows. So picture yourself, you created a view of all of your videos with all of the frames, but now you wanted let's say you had a model that would identify frames where it's raining. And now you want to do something specific with just the images of these rainy scenes. So you could create another view on top of that that is defined with a predicate of the underlying table. So you can simply string together this kind of hierarchy of views that conditionally select something from the base. And you can then, of course, add more computed columns to that view and through that mechanism basically get conditional data flows, right? So all of these computation then only happen on the subsections of the data for which they are defined. So here we have a speech speech generation from the transcript text for a particular view. Um, Another very interesting aspect, and I mentioned that before, Pixeltable has a concept of iterators. And so the idea being that you often want to go from, let's say, videos to frames, or from documents to text chunks, or in general from a larger object to components of that larger object. And for that, we have basically in the database world known as lateral views, basically views that take a row from the base and blow it up into multiple rows on the view. And so here we use the string splitter as an example to define a view of the base transcription text. And the transcription text can be very long. And now we created a view that splits on sentence boundaries and gives you a row per sentence. So if you want to do anything with the sentences, it is very handy to have a table that contains one row per sentence. So this is what this will give you. And we'll see more examples of that later, in particular with videos into frames and so forth. You can also, there's another application, let's say, for medical images, they're often gigantic and you want to be able to tile them so you can do something with them. They're often like 20,000 by 20,000 pixels. So
Well, the sentence view, is that punctuation dependent, or is it doing some amount of semantic analysis? Say, for example, you gave it a set of text messages and someone was being sloppy with their communication.
yeah. It's using Spacey under the covers, so it depends on whatever NLP model you have. Again, this is something you can do yourself. So Pixeltable is not comes with a bunch of prepackaged functionality, but it is not limited to that. So if you have a specific application and you need to break up text messages in some particular form, and you understand how you need to do that, you can simply write that as your own user-defined iterator and then utilize it in this context. So you are not limited by Pixeltable's built-in functionality. Pixeltable will give you the data flow, so it'll automate the data flow and it'll populate the persistent tables that contain the chunks and so forth. But if you decide you need to chunk your text messages in some particular way, you can still do that with Pixeltable, even if it is not supported by the built-in sentence splitting.
Gotcha. Yeah, and not to deep dive too much on the functionality of Spacey, but I guess maybe another example of weird sort of sentence fragments is in media, sometimes someone's interviewed and they get to a point where they sort of think about what they're saying and then sort of chop their sentence up. I suppose that's something that would end up in just another table row.
I'm not sure what Spacey would do with that, honestly.
Gotcha. But if
You
they
would have
did
to,
it right, it would end up in a new row in the table.
um, potentially, yeah.
Right.
Again, I mean, Spacey works on just the text. So if it is a transcript that contains a bunch of filler words and stuff, not exactly sure. Even pauses, it probably wouldn't take the pauses into account if it's still turns into coherent text. So
Gotcha. But yeah, this is not a presentation about spacies.
yeah, yeah.
I had
So
a
here's an example.
Oh, I heard a question, Nitin.
yeah. So I was wondering, maybe you already covered it, but I know you're combining both the storage and uh, the orchestration. But how well does it combine with, let's say, if you wanted to use stuff from LangChain or from FAIS or anything like that?
What from LangChain in particular?
Oh, for instance, I mean, one thing I was thinking about was a recursive text splitter, for instance, is a pretty handy tool for doing the splitting as opposed to spacey.
Okay. Um, yeah, I mean, you could, if you wanted to, you could probably take your LangChain splitter and adapt it and just give it the basically implement it against the Pixeltable iterator API. We might just add recursive text splitting ourselves, but yeah, you can absolutely do that.
All right, thank you.
Does that answer your question?
Yeah, it does. So you can just take particular modules off of LangChain, for instance, maybe a bloated piece of code if you're using multiple orchestrators, but you can do that if you needed to.
Yeah, you could. Yeah, exactly. Again, you would need to interface it to with the Pixeltable iterator implementation. So so the Pixeltable runtime is able to call the iterator and basically get the output and know what the types are and stuff like that. So Pixeltable is strongly typed internally as well.
All right, thank you.
Um, oh yeah, lateral views for videos. So here's an example of a frame view of a table containing videos, and FPS 0 in this case means full frame rate. And so this is what it looks like. You creating a view, and you can now basically see the frames with some of the metadata, such as position and the millisecond position and so forth. Um, Indexing is also covered by it. So the way you do it is you add an index on a column. So you don't have to think of the index as this other thing that sits somewhere else and you have to feed it repeatedly from a pipeline. You just add it, and then the system maintains it as you add more data to the underlying tables. So in this case, we're adding an embedding index on the frame column. And you can also now specify what model you want to use. So in this case, we are using clip from the built-in Hugging Face clip UDF. And so here you are special casing it or specializing it by providing the model ID. So this will guarantee that all subsequent insertions into the table will compute an embedding using exactly that model. And when you run a query now with like so here's the frames.frame is the reference to the column that you have here. And we're using the pseudo function similarity and giving it, asking for a black tie. And so this string black tie will be encoded with the same model ID as the one used for the index. So you do not have, there is no opportunity for you to shoot yourself in the foot by accidentally using a different model for then running a query against the vector index. And so here's the query. You just order it by similarity and select whatever you want from the table. Um, I mentioned before that Pixeltable is very extensible, so there are various avenues for adding user-defined functionality. There is the user-defined function, which you use as just a decorator on a function that basically takes a bunch of scalars and returns a scalar. Then you also have user-defined aggregates, which are defined on classes, and they basically do exactly that. You can use them to aggregate data, such as aggregating a sequence of frames into a video. That's also considered an aggregate. Just like, if you're summing up a bunch of integers, that's an aggregate. And so you can make videos as well. And you can also aggregate audio and so forth. There's also then the user-defined iterator, which goes in the opposite direction and takes something larger and turns it into pieces, right? So it takes basically one data item and turns it into a sequence of data items, sort of the inverse of an aggregation operation. Um, for if you're doing model training, which is was one of the motivating use cases for Pixeltable, was basically how do ML teams work together to do data set curation for model training. And so what is really important in that space is reproducibility and lineage, basically observability. And so in Pixeltable, all table operations create new versions. So if you add a bunch of rows to a table, it will create a new version. And you can create snapshots of tables that will basically make sure that the underlying data in the snapshot never changes. So you can always query the snapshot. And you can also now revert changes to a table and it'll restore the previous state. So here on the right-hand side, we're creating a snapshot of the frames table, and then we're deleting data from, so frames was a view defined on a table called videos. We're creating a snapshot of the view. We are now deleting all of the data in videos. And so that means that the view frames now also has no more data left. Frames.count is 0, whereas the snapshot contains the everything that was in it previously, as you can see. And then if you then revert your changes on video, this is again the base table of frames. You are also getting back all of the data in frames. And so you can see that it got restored to the previous state and now again contains almost 1800 frames. I'm again going to pause here to see if there are any questions.
I have a question about an implementation of a project type that I'm working on, but I think maybe it makes sense later once you cover a couple more concepts.
Okay. Um, Here is what it looks like to use data sharing through Pixeltable. So as I mentioned before, the initial version of it will allow you to share tables you created locally by giving it a Pixeltable cloud URI. And you can think of that kind of like a GitHub for tables. So here we have a table that is under this particular URI. We're creating a copy of that table that lives in the cloud, and that copy then functions like a regular local table. So what'll happen is, actually, let's look at the example here at the bottom, which logically precedes it. You have a table here that contains videos, and now you publish the table under a particular URI. And that means that people you collaborate with can now get a local copy of that by replicating that URI. And that local copy will include all of the media files as well. So however complicated your data set is, it'll basically include all of the media data that is part of that table.
So if access is private, how does that work?
Uh, in what way? Yeah, then you have an account, and you can do that as part of an organization. So we're working with a bunch of design partners that want to keep their data private, but they want to share it within the organization.
So if it's public, that means then any data.
Anyone can look at it. Kind of like public GitHub repos. You can think of it like that.
Okay.
Yeah. And there's a whole bunch of, I want to say standard data sets that are used in various places that are available publicly, like Hugging Face has a whole bunch of data sets that are public. And so Pixeltable will have something similar, except that when you then replicate it locally, you can immediately work with the media data. So it's already in a basically form that you can then work with directly. Okay, so I'm gonna wrap up the presentation portion of the evening. And so, some key takeaways here. It is a single system. Pixeltable is a single system for all data storage. In particular, it includes your media data and ML-specific data. So no more trying to figure out how to distribute your data across three different types of storage managers and then having to pull it all back into one system or look up one piece based on another. Um, there's a single API for all data access, and that's also very important. So all of the data generated through computed columns end up in tables and is queryable just like the data you started with. So there's a single query API for all of the data that you either input directly or is computed in Pixeltable. And that is an API that very much mimics standard, I want to say, relational database system functionality. And another interesting aspect is that because of this persistent table structure, you basically have observability built into the system. So a table itself is in essence a log. If you think of computed columns as running a pipeline, you will, by virtue of them being computed columns, um, all of their output is stored in the table. So that is kind of like saying if I do a pipeline, I have all my intermediate data also stored and observable after the pipeline runs. So the schema basically expresses your orchestration. And when you run something through Pixeltable, it will then store all of the intermediate output and it is persisted. And you can query it through the same table API that you use for the input data. And another aspect is that because the system understands the computation and the dependencies between the computed columns, it can now also parallelize the DAG evaluation and basically achieve minimum latency and maximum throughput, right? So in essence, similar to how a relational database system would take a SQL query and then optimize it to minimize execution cost, Pixeltable can do something similar and minimize basically latency based on parallelization at runtime. So, and again, these are things that you get for free in essence when you use the system, and that are very hard to accomplish when you have to hand code all of that. Um, Here's how you get started with it. Like I mentioned, it is locally pip installable and comes with Pixeltable actually has fairly few dependencies, which is something that differentiates it from something like LangGraph. And if you install it, it'll install a custom version of of Postgres and run it as well. There's also, like I mentioned, the Pixeltable data sharing cloud for which you can sign up here. And oops, and this is the below here at the bottom is the repo that contains the demo that I'm about to give. So Woody, feel free to distribute that link
I'm on it.
in your user group. Okay. Um, some more resources here. We obviously have a GitHub, a bunch of sample apps. There's also an MCP server. We have some sample, I want to say projects based on it. One is basically an agent that uses Pixeltable for memory in essence. It's very easy to roll your own agent framework with that. Most agent frameworks basically try to figure out how to store data and then refer back to it in multi-turn interactions. And there's also Pixelbot, a sample implementation of such an agent that is able to memorize, remember videos, and so forth. And so basically does multimodal indexing. Um, okay, the booth. This is from a previous talk. And now I'm going to switch over to the demo portion of the evening. And I'm doing that by joining from my desktop. So bear with me. Okay. And I am going to share. Oh, okay. I'm gonna stop sharing here and start sharing on my desktop. We are sharing this one, and it is tiny, and I'm gonna make that a lot bigger. How is that? Is that good?
Looking pretty good. Could you zoom the text in a little? You Control
Uh,
plus or Command plus?
Sorry, like so?
Oh, yeah, much better.
Okay. All right. So, yeah, Pixeltable, you would typically just import it as PXT. Here it is, and whoops, what happened here? Oh, I am sorry. Let me let's import. I messed up my environment, but I'll fix that. Okay, here we go. There it is. And so the first thing we're going to do is we are creating a table with videos. So again, just to set the stage, we are trying to index our video content by indexing the audio and indexing transcripts and indexing the frames. So a bunch of indices, and we're going to demonstrate how to basically put that pipeline together. So we're starting with a table that has a single column video, and we are now inserting a single row with this URL. So this is a um, trailer for Stanley Tucci's show. What's it called? Something about eating in Italy. So we're going to insert that now. And what that does is also does a transparent download and validates that it's actually a playable video. So it's trying to ascertain that the data in your database is correct. And so here we can see the schema of that table contains a single column called video of type video. And if we run a query, t.collect is basically saying, give me everything back that's in this table. And so now we see here there's this video, it's the trailer for the show, and it is a playable video. All right. So we got that. The next thing we're going to do is we're going to extract the audio and then chunk it into 30-second pieces. So first, to extract the audio, we are using the built-in UDF extract audio that acts on videos. And so this is what we're doing here. We're creating a new computed column audio that does the invokes the UDF. And so here we go. We have created a new computed column. It did the audio extraction, and this is what it looks like now. We now have a table with two columns, one of which contains the extracted audio. So it tells you not just that it's an audio column, but also how the computation happened. And so then we're going to go back and add another computed column to get the metadata out of the audio. And so now we have two computed columns. And again, you can see how the audio MD column is defined by get metadata. And so let's take a look at that. So now you have here the three columns in that table. And this, again, is a playable audio file that just got created. And here is the metadata of that audio. So you can see here that it is duration seconds, 110 seconds long, almost. So now we have in the original video table, we now have computed columns, audio, and the metadata. And now we want to turn the audio into 30-second chunks. And we're going to do that by adding a view that utilizes the audio splitter. So here, the audio splitter as an iterator in Pixeltable. And if we run it, it is created four rows. So, of 30-second pieces, I guess it's a little bit over, uh, uh, a little under for 2 minutes, sorry. And so what this does is basically says create chunks of duration 30 seconds, which is what we did. And so now we have a view that contains these four columns predefined from the splitter. The position, so because it is an iterator, it basically tells you it starts at position 0 and then has 1, 2, 3. So you basically can reconstruct what you were iterated over. And it gives you the start time and the end time in seconds of your audio chunk. And then it gives you the actual audio chunk as audio data. And one thing you also see down here is the columns of the base table repeated. So in essence, in the view, you can access the base table columns and it basically gives you an implicit join. So if you need to use the anything such as the audio metadata and so forth, you have all of that available as well. And so let's take a look at what this looks like. So here we have the first row in this table is position 0, the audio chunk from 0 to about 30 seconds. And again, you have a playable audio chunk. And here it just repeats the video. This is again from the base table. So you have basically access to the video and the entire audio extracted audio. So there's that. Um, any any questions here?
So is there a chunk that has some dialogue in it? I suppose that's maybe coming up so we can see
Yeah,
descriptions.
it's coming up.
Okay, cool.
Let's take a look at yeah, let's see what happens now. Also, when we extract the audio, we create new media files, and these are stored and accessible as regular media files, which you can see here, they're MP4s, sorry, WAV files. Um, if you want, we can also put them in a different destination. So there is implicitly in the local pixel table, there is a slash media directory that is the target for all generated media. But you can actually set a media destination and then it'll dump newly generated media files into that destination. So if you wanted to use that to create servable media data, you could put that into a different directory. Um, so
Marcel, so just chopping it up into 30-second segments, it seems like the most useful would be it would detect silence, right? And then identify the sections where you're actually talking. But so presumably there are functions like that, and you can plug those in, right?
you could. I mean, our audio splitter is today only based on duration. Oftentimes because when you're using external transcription endpoints, they're often limited on duration.
Okay.
But you're right, right? Detecting silences and so forth. And there, WhisperX might be a good thing to run. I think WhisperX does diarization and gives you timing and so forth. But again, this is really a question of the model, which is not built into Pixeltable. So whichever transcription model you have, or whichever, let's say you have audio functionality and you can use FFmpeg to detect silences and so forth. So you can also do all of those things. Again, we're trying to build useful functionality into Pixeltable, but we're not trying to be the authoritative library on anything audio, basically, right? So, but yeah, if you have specific audio needs, you can use them, you can implement them as UDFs, and or you can also contribute them to Pixeltable, such as, a splitter on silence could be interesting. Um, let's see. We talked about this already, and we also mentioned that everything here has a local path, so they are actually real files that you can then utilize elsewhere. We now have a view that contains these audio chunks, and what we want to do is transcribe them and then index the transcripts. So we're adding a computed column here to the view with the audio chunks, and this is doing the transcription. So it is calling the built-in user-defined function OpenAI.transcriptions, which maps onto the transcriptions endpoint. And you are passing in the audio chunk, the one that you just produced. So this is nice. Pixeltable now understands where the data lives, and is able to then feed it into the model invocation. And so here you are picking a particular model. And so we're going to do that now. And because it's calling the external endpoint, it's going to take a little while. And there it is. All right. And so now you have in V1, now you have an additional computed column called transcript. And you can again see here how it was computed, right? You called the transcriptions endpoint on the audio chunk. So audio chunk, this column, transcript utilizes that column to produce the transcript. The transcript itself is, let's take a look, v1.collect. Actually, that's not a good idea. Let me do v1 head 1. And this is what you're getting. And you can see here that the transcript, let's actually do this, v1.select, transcript. Here we go. This is the actual JSON output of the transcript UDF. And you can see here it's JSON, it has a text here. And then there is a bunch of stuff like, things you might find interesting or not, like usage and, log props, null. I guess you can ask for stuff. So, and then what we did here is we're adding now a computed column, transcript text, that simply contains a JSON path expression to pull out the text as a separate string column. So here you need to tell it what the actual data type is. So we do that, and now we have both the transcript and transcript text computed columns. And so this is what it looks like now, right? So here you have the transcript text pulled out directly, and now you can work with a string.
Now that's without the speaker diarization that you referenced, right?
Yes.
Which
Yeah,
is to say, for anyone who's interested, that's sort of who spoke and when.
Yep.
Yeah, because like the transcript seems pretty accurate, but also it's kind of silly. Like if you think of it in a single speaker's voice, now I'm more hungry. Me too. Like no one talks
Yep.
like that individually. But that would just be, a separate plugin or something like that.
Yeah, you can use WhisperX
Yeah.
As a UDF. So now we have the transcript text as a computed column, but we don't want to index the entire transcript because that's too long. So now we want to split the transcript into sentences. So that's what we're doing in the next view. So we're creating a view on top of the transcript of the audio chunks view. And this one is called transcription chunks. And it uses the string splitter to split on sentences. So we're going to do that now, which will download Spacey's model for detecting sentences. And so here we go. So now we have a view v2 only, which defines as new columns here only the first two. These are again all repeated from the base table, right? Remember v2, the transcript chunks view is defined on the audio chunks view. And so the audio chunks view contained these columns, start time, end time, audio chunk, etc. And so you have access to these here as well. So again, there's an implicit join from the view to the table it is referencing. And so now we can look at, here we go. We can look at the sentences that it got split into. So this is one transcript from one audio chunk. And here are the sentences, right? 1, 2, 3, 4, right? This is sort of based on sentence boundaries. So here you can see that you were able to break up the transcript into these sentences. Here's another thing to look at. Here are the first sentences from each of the audio chunks, right? And so now that we have the the transcript chunked into digestible pieces, we're adding an index using a sentence transformer model from the Hugging Face lineup, and we're adding it to the text column of the transcript chunk view that we just defined. So we're indexing individual sentences from the transcript. So here we're going to do that, and it did. Okay. And so what you see here at the bottom, we still have V2, still has these two columns, position and text, but it now also has an index using a cosine metric using this particular embedding function. And again, you can bring whatever embedding you want, right? If you have specific embedding models, either through an external inference provider or that you want to run locally, you can use those as well. They just have to be interfaced with as a UDF. But if you have that, then you can use anything you want here. And so here we're going to do a similarity search. So the index was defined on v2.text, and we're going to use the similarity pseudo function, and we're going to pass it a string heritage. So this string heritage is going to be embedded using the same embedding model that we defined up here. So this is kind of something that the index does for you. It'll use the same model, and then you're going to basically run a query that simply looks for orders by similarity and then does a regular query and returns a bunch of stuff. So let's see what that does. Heritage, we pulled out of V2, so the text chunks that we have, things that kind of to clip look like the term heritage. And so you have this stuff here, you have sustained this culture for thousands of years, sounds like heritage, or character and history, and so forth. And you can see that because of the implicit join with the base table, you also then have access to the actual audio chunk it originated from. So that's one piece. So what we have now is we created two views, one containing audio chunks and another one on top of that containing the sentence pieces of the transcript of the audio chunks. And now we're also going to split the video into frames by using the frame iterator. So here we are creating a new view that gives us 1 frame per second of the video. So let's do it. And that takes a little longer because it has to do video decoding. And here we are. So now we have a frames view. And again, every one of these views has a position column, but now it gives you a bunch of metadata about the frames, frame index, and so forth, and the actual frame as a pill image. So here's what that looks like. Here we go. You have, frame index, position milliseconds. So this was defined with frames per second of 1. So you now have every 1 second, you have a new frame and you're getting the actual position of the frame. So here you see Stanley Tucci wandering around some Italian city and looking at, a bunch of composed dishes. So here we go. And what we're also going to do now is add an embedding index on the frame column. So here, again, adding an embedding index to the frame column using a clip model again. And because clip is defined both for text and for images, you can now use both text and images to run queries against that column. So let's do it. And a bunch of output we don't care for, but and here it is. Okay, so now we're going to do some search. So now we have an index on V3, and I'm going to do that again, V3. And we see here, down here, that we have an index on the frame column, again, using a clip model. And so now we're going to do an image search using an image. So the first thing we're going to do is we're going to pick out some frames that we think are interesting. And so here we're looking at frames 75 to 80 frame positions. And just to get something that looks kind of interesting. and we settled on frame number 78. So Stanley, glass in hand, someone's drinking some wine. Good for them. I wish I had a glass in my hand right now. And
Next time, if we do it in person out in
there you go.
Oakland.
And so what we're going to do here is we just ran a query where pause equals frame pause, where pause is frame position number 78, and we selected the frame column, and we got it back as so sample frame here is a pill image. So we were able to retrieve an in-memory pill image using Pixeltable. So here, let's see if I can, nope, where b pause equals 78. Let's forget that. And I'm gonna hang on, okay, type, what do we call it? Sample frame. Sample frame is a pill image. So here, Pixeltable gave you back an in-memory pill image. And now we're going to use that again for the pseudo function similarity, and we're going to hand it the actual pill image and see what we get. And here they are. So, first position, similarity 1, no surprise, the original frame. But now we have a whole bunch of other images where Stanley is near a glass and is, surrounded by people. So seems like that worked. And now we're going to do something similar, but now use a string, in this case pasta, to query the same frame column using the same similarity function. So here we're passing in the query text, looking for pasta, and here is pasta. No Italian food show without pasta, obviously. So yeah, so this is kind of demonstrating the power of vector indexing, but without you having to worry about when to run the embedding function and so forth. And we're going to leave that out and instead are going to do now the incremental updates of a table. So here we're going to insert a new video that is also from Stanley Tucci's Italy series. And we're going to insert a new row into the base table, and we will now see it then populate automatically all the views we had defined on that. So we're going to add that. And sorry?
If I could just interrupt for a second. So you're in order to find similar images, you're relying on the voice narration and the transcript of the voice narration, correct?
I'm not totally following. What are you referring to? To find
So
similar, you mean here, up here, or is this
yeah.
the voice narration? Not terribly. I mean, this is still using the index on the frame column, right? So you're providing a sample image to the similarity function, and you're querying the frame column here. So this is that V3 frame, and then you're saying similarity, and you're giving it the sample frame you picked out earlier. So this is not yet. We could also run a query against let's see, the index we put on not frame, sorry, I have to backtrack.
You have a default function
The
for
index we
comparing.
put on V2 text, right? We could also use that now, actually with an image, but I don't think the glasses will yield much, but we can see. Did that answer your question?
Okay, so one thing I can tell is that there's a voice or there's a audio transcript, right?
Yep.
And there is actually a image comparison, a default image comparison function, which presumably could be overridden with a different comparison function.
Let's see. The image comparison function. You mean the similarity function here, or this one, or what do you mean?
Yeah, so it just says frame.similarity, but I don't know exactly, what algorithm it's using to determine that.
Yeah, it's basically cosine similarity based on the the embedding index is using PG vector in Postgres. So that's again, this is an approximate nearest neighbor search, and it is not an exhaustive search through and a comparison. It doesn't compare every single frame in your table.
Right. Yeah. Thank you.
Um, all right, let's go back to here. So what I just did is I inserted a new row into the base table. And you can see it now that inserted that one row into the base table and then also populated all of the frames. So all of the views. So we had the audio chunks view. And apparently it's something that is about less than 1 minute of audio. So it created two new rows for the audio chunks. It also put four more rows into the transcript chunks. So it broke that up into sentences. And then it also added 31 more frames to the frames view. So about a 30-second clip here. And so you now have the base table updated with, there is another row here. And you can see view one, which is contains the audio chunks, now also contains, we inserted this URL called searching-italy.mp4. And you can see here that when we look at view V1 with the audio chunks, looking at the file URL here, this is the new video that was just inserted, and you can now get the audio chunks out of here. It was exactly 31 seconds, so you have a 30-second chunk and a 1-second chunk, right? Here's the transcript text for that chunk. The same is true for view V2, which contains the text, the sentence chunks of the transcript. So if we look at that, again, here searching Italy for this new video, we have the sentence, the transcript text, the whole transcript text. And here is the first sentence from each of the chunks. So again, the derived tables were all populated automatically using the way they were defined previously. And here we are looking at the frame view and looking at the last 5 new frames, again, coming from the new Searching Italy video. And so here we have 31 new frames, and here they are, right? The end scene and then a bunch of credits. That's what we get. So yeah, so this concludes the demo. Basically, I wanted to show how you can build a fairly complicated pipeline that extracts various pieces of data from videos, the audio, transcription of the audio, the chunks of the transcript, as well as the frames, and then actually creates searchable indices on those. And you now have a system that can then also be updated incrementally. So if you just add more videos to the base table, it will populate and keep up to date all of the views and all of the index structures you have defined on the views.
Very cool. It seems someone could potentially find the right plugins to take a video and output a script, from a movie script as a result, if they
You
were
can
clever about it.
probably do a lot with LLMs, yeah.
Yeah. So I had a question earlier that I alluded to, and I just wanted to make sure you had a chance to finish. I was wondering about, I've been working a little bit in 3D. The technique I've been working on is Gaussian splatting. And so you take a video feed or multiple video feeds and do the Gaussian splat, and then you output a point cloud and or a 3D model. So I'm wondering, how would an implementation look like for that? Say, for example, you had some scene that's going on, and multiple individuals had their cell phones out and were streaming video. from it? Maybe say you're at a concert or something and you've got a handful of people generating video. Is that something that could be coordinated using Pixeltable?
I guess I'm missing what's the coordination piece? I'm not totally sure what exactly you're doing.
So there's a endpoint that perhaps is or isn't integrated with Pixeltable yet called Luma AI, and you can input video into that, and then it'll process that and output any number of 3D files, point clouds or whatever. So I'm wondering, is that something that could be done, or is this typically a singular input and then, sort of tabulated multimodal data?
No, it could be. I'm not sure. I would have to look at the specifics of the endpoints if the data types are compatible with Pixeltable. We don't have point clouds just yet. In principle, we could also add that as a media type in a sense. So I'd have to look at it in detail. But in principle, like if the data type is supported, you should be able to just add it as a UDF, and then you can, call it and add it as a computed column.
Okay, interesting. Cool. Well, this is amazing. It's really, really neat how you've taken a simple thing as a table and made that into an interface that sort of parses things down into their constituent elements. This is great. Anyone have any questions for Marcel?
I'm wondering if you'd want to see the MCP, because that makes it really easy for developers to use Pixeltable. I could demo it real quick. Put it up here on the screen if you guys want to see it.
Sure, you should be able to share if you want to go ahead.
We're on the right screen. Can you guys see the screen? It sort of disappeared from my.
Yeah, if you could zoom in the text, that'd be great.
Over here on the right?
On both sides, if possible. I'm seeing a ghost.
A web browser.
Yeah, I see Chrome, and then I see an IDE of some sort.
Yeah, so on the right-hand side where I'm typing right here, this is just Claude Code. And I have the Pixeltable MCP developer plugged in. And then over here on the right is just a browser window that uses the MCP's integrated canvas. So you can use this to just explore and look inside your local Pixeltable instance. So if I want to list the tables, I can do that. I can do basically any of the notebooks that are on the Pixeltable repo. This MCP has those integrated. So it will, it's trained on those. So you can basically build a RAG or do video or do object detections, just working with Claude. So I just asked him to list the tables that are in my local setup. But I also have here some sample files, so audio, video, PDF. And I can say, Claude, make a table from the videos. And make a new table. So this just gives you a language interface to Pixeltable to comfortably do basically anything with Pixeltable. So I've given Claude a access to the Python REPL, and also this connects to the Pixeltable documentation. So it's aware of how everything works with Pixeltable. And so I've just asked it to add some videos to my Pixeltable and a new table. And it's just going to go grab those videos from my local file system and add them in, and then create a table from this. haven't actually tried this yet. So hopefully it'll work. I think it will. Yeah, there we go. So it just added those videos from over here into Pixeltable. And then if I want to run a model on these or do a detection, or I can just ask for it. I haven't worked as much with the video features, but it works great for the audio and image and PDF. Like if I wanted to make, just while we were in this meeting, I made a quick rag from Pixeltable, some PDF file. So I can say, hey, could you display the data from the PDF extractions? And it should be able to do that.
This ghosty thing is running just on your box there?
Yeah, this is just Ghosty is just a terminal program. It's really nice. I think it usually ships with Linux.
Oh, cool. I posted
it's
a link to it in the chat if anyone's interested.
So now I'm just saying, earlier I did like a little rag real quick with Pixeltable. So I had it ingest PDF files and then chunk them and then make embeddings while I was watching the demo. And so here's the output from that. Like it looked at these PDFs and chunked them and then showed some of the data. And then you could also show the embeddings for it. Oh, it's actually doing that. It's saying it's going to show me the text with the embeddings. So yeah, so this is trained on all those notebooks. We kind of set up a system where all the notebooks that are documented get fed into the system. So the LLM knows how to use Pixeltable and implement any of those developer patterns that are described in the notebooks. And what's kind of cool if you're into LLMs is I had the LLM come up with new developer patterns that weren't in the notebooks, things that it thought people might want. And it can create new notebooks from that, which is really pretty amazing in my mind, because it becomes a self-learning system where it creates new notebooks. Or if you have, like, say you read a research paper and you're like, wow, like I see a lot of papers out there that are like, this new agent system is self-learning and it can do X, Y, and Z. You can just go into this MCP, you can give it the PDF from the research paper, and you can say, can you implement this in Pixeltable for me? And it'll build a whole agent system. I mean, that's what I think is really one of the strong things about Pixeltable, is that it just has access to all the models, all the tools, and this MCP automatically will download them and handle it in the background for you. I've also started working on a new, MCP is nice, but it's a little bit of a hack because it's like using the Python REPL in the background and stuff. But Anthropic has a new Claude SDK. And so I've created a whole local system. You can also do visual stuff too, where if you wanted to like, it also does mermaid diagrams. So if I want to see the structure of tables, so this is looking at my pixel table and it's going to make mermaid diagrams of, some of the tables in there and their relationships. You can also output the code that you create into a repo. So like if you set up a really cool computed column or a UDF, it can save that to your local repo, and then you have it. You can always rebuild that later. So this shows like, here's my base table of space images, and it has a computed column. It shows, basically all the relationships that are happening in the background when you use it. Or here's space images with computed columns, does YOLO detections, strings. So this is just like an easy, comfortable way for you to actually use Pixeltable and prototype applications. You know, you could make your first application, and then with the sharing features, you could share that out to the web and have a production ready application.
Very cool.
I also just made a TypeScript interface to Pixeltable. So if you're making web-based apps and you're happy in TypeScript, you can use that to connect through to Pixeltable. So this shows how this works. There, we got PDF, we got video samples, audio samples, space images. This is basically showing how this actual canvas display works. But it can do free form using that data directly. So if there's anything you want to see or do with Pixeltable, you can do it here through a natural language interface. And that's available on the, I think you shared the link already. It's MCP server Pixeltable developer. The important part is the developer.
Yeah, if you just scroll up in chat, there's a link to that.
And if anybody wants me to try to do anything with this right now, just randomly, just give it a shot, like anything you want it to do. I've got loaded images, videos, audio, and text. So we could try something if you guys are curious if it'll actually work.
So the example I thought of is from the movie Monty Python and the Holy Grail, right? I want to find the scene with the holy hand grenade. So I want to find the start and end times and give me a convenient way to access that. So how difficult would that be to do?
In theory, it wouldn't be that hard to do as far as any of the models. I don't have the keys for OpenAPI and stuff plugged in, so I can't demo that right here.
Right.
But
yeah, I mean, you also need. I was going to say you also need the actual movie.
You wouldn't need. That's that's the easy part.
It would take
right?
more than a few minutes, so I don't think I think it would be a fair amount of processing to churn through, to chunk the whole movie and churn through it.
But in theory, totally doable as long as there's the models for it and you can describe it in language. It's doable. If there's not a model for it, like there isn't currently a model that can do that kind of scene detection, it might take a little bit more hacking with Claude, but you can still do it. There's ways to do it.
So my assumption, the naive approach would be it sucks in the whole movie, which should be doable, right? With Pixeltable.
Yeah, we just did that here.
Then it goes through and extracts all the audio and transcribes it. Then it looks through the transcript until it finds the keywords and then notes the timestamp. And then from there, you know where to go into the video column to get the corresponding video.
I think that would work. It would take a while because it's a 2-hour movie, and so you'd be chunking it through and then processing the audio transcriptions of the segments, and I think it would work. And you could, you could even think of it a little less procedurally. You could think of it as we're going to construct a table with the segments of the movie transcribed, and then once we have that table, now you can just run queries against the table. So searching for that particular scene would be a query against that table, but you'd have all of the data in the table. So if your next question was, okay, now I want to see the scene with I don't know what's his name, the sorcerer, Tim the Enchanter. I won't give me the scene with Tim the Enchanter. It would just be another query against the table, and that would be very fast. So you'd have the data sort of prepared and indexed in Pixeltable at that point.
Right. So for a long input file, you just have to suck it up with the processing cost to index it. If you have a bunch of small clips, then that would seem like they would be a natural for this.
Yeah, I mean, either one's a natural for it. So there's nothing, what do I want to say? I mean, there's nothing wrong with having large media content that takes a while to process. And it's not, Pixeltable isn't any better or not better suited to media of a particular length or size. So I don't know. It's kind of agnostic about whether it's a long file that gets chunked or a bunch of short clips. So
what happened?
That it was going to take a while, that is to say, was not a comment about Pixeltable specifically or the fitness for Pixeltable, but just, if you have a 2-hour movie, it's going to take some time to process that.
Okay.
Yeah, I think that's a good segue into a question that Steven asked in the chat. He says, how much is the AWS bill for processing a typical 90-minute movie? Ballpark on that?
We can't really speak to that. I think AWS probably has some specific services around that, but I don't know. We don't know. And again, it depends on what kind of processing you do.
Exactly. Yeah, depends what you're doing with it.
You can do a lot of local, speaking of scene detection, we actually just added scene detection UDFs. So you can actually do some scene detection algorithms and use that now for chunking a video into scenes. And then you can index, if you wanted to, you can index just a select number of frames from a scene, right? If you just want to do like first, middle, end or something, you could do that.
Yeah, I mean, that's one of the beauties of Pixeltable being open source too, is that, if you create something, you create a UDF or you solve a problem, you can always share it with the community and it becomes part of the system and, solves a problem for everyone.
Well, this is really cool. We are at the end of our time, and I want to be sensitive to people's evenings. So once again, Marcel, thanks for the presentation. This is really amazing. You and Aaron have done some great stuff. And Ross, thanks for coordinating. Would love to see what happens in the future. If you have any future releases, we would be more than honored to have you on again. So thanks again, guys. And Aaron, we will see you in a month.
Thanks for having us. Bye.
Bye, everyone.
Thank you, everybody. Thank you. Bye today.
Bye, indeed.
Thank you.
Bye.
See you later, all.
Take care.